Okay, well, thanks very much for the invitation to speak. It's a great pleasure to do so. So today I'm going to talk about some joint work with Yuanpu Liang. So Yuanpu was a third-year undergrad when we started this project. And so when he asked me if I had something he could work on, I had this lovely paper by Michael Hutchings and Jean Gutt on my desk, which contained these concrete formulas for a sequence of capacities that they constructed and conjectured were equal to the Ecklen-Hofer capacities. So I suggested we take a look at these. And then we had what I considered a long kind of run of good fortune, where we were able to derive some clean answers to concrete questions about these capacities. They're kind of hands-on and easy to talk about, so that's what I'm going to discuss today. So let's see. Sorry, my computer's not responding. There we go. So I have to start with the definition of a capacity, I presume. So this has several variations. So here I'll just consider subsets of R2n, or a class of subsets of R2n. And a capacity would be a map onto 0 infinity with the following three properties. We have this monotonicity and invariance properties. So if there exists a symplectomorphism taking a set U inside a set V, then the capacity of U must be less than or equal to the capacity of V. Any capacity will scale with degree 2. And then we have these familiar conditions. The capacity of a ball should be non-zero, so that it's a non-trivial invariant. And the capacity of infinite symplectic cylinder should be less than infinity. All right, so it's, usually we don't start with that last one because it's possibly strange to introduce a measurement with such a big blind spot, but of course that's part of the point. And a symplectic invariant is meant to be, or a symplectic capacity is meant to be something which captures some type of non-squeezing. Oops. All right. So just the standard examples for reference. We have the Gromov width, which is the supremum of the cross-sectional areas of balls that you can symplectically embed inside your set. And then we have the kind of first set of capacities defined in terms of Hamiltonian dynamics due to Ecklen and Hofer. So there's an infinite sequence of these, and these are defined for all subsets of R2n. And then the capacities I will consider in the talk are those constructed by Gutt and Hutchings. So I'll just denote them by CK to keep the notation simple. And so these are defined for star-shaped subsets of R2n. And they were defined using S1 equivariant symplectic homology. Given the full machinery of that object, their definition is very simple. In kind of the generic case, when, let's say, the star-shaped hypersurface is transverse to the Liouville vector field, they're defined as spectral invariants. So the symplectic homology of any star-shaped domain is always the same. It's Q in degrees with the same parity as n-1, and otherwise it's 0. And then the capacity is defined using the action filtration on the complex giving this homology. So if we restrict actions, say, to less than some number L, we get another homology. This very much depends on X. And we have an inclusion map of this homology into the total symplectic homology. And the kth capacity is defined as the inf of L, where this image contains the non-trivial symplectic homology in degree n-1 plus 2k. So all this is probably very familiar. In the paper where they introduced these capacities, Gutt and Hutchings conjectured that they agree with the Eklund-Hofer capacities for star-shaped domains. I don't know if there's been any progress on this. Well, I know there's been a bit of progress on this, but I don't know if it's settled. But they verify this for symplectic ellipsoids and polydiscs. So I'm just using the standard definitions for these objects here. So E1A is defined in the usual way, and it's the Gutt-Hutchings capacities agree with the Eklund-Hofer capacities, which are these numbers. So the kth capacity is the number one gets by taking integers and the union of the integers and the integers times A, sorting them by size with repetition and taking the kth element. And then the symplectic polydisc, the kth capacity is just K. So here, of course, I've chosen A to be greater than 1, but not set it. All right. And so these computations that Gutt and Hutchings presented are smaller examples of larger computations they produced. So they established formulas for their capacities for convex and concave toric domains. Here are the relevant definitions. So we have the standard moment map from R2n to the non-negative sector in Rn, which takes Z1 through Zn to pi norm of Z1 squared, pi norm of Zn squared. And then to a domain in the non-negative sector, we look at its preimage under mu. That is a toric domain and x omega, and we say that it's convex if omega hat is convex in Rn. So omega hat is this kind of set which of points whose absolute, so if you take the absolute value of every entry, you get inside of omega. So that has to be convex. And then they define the notion of a concave toric domain as one where omega's complement is convex in the non-negative sector. This was done, so such sets were studied previously for embedded contact homology capacities. They have lovely properties. You can see the Lagrangian tori that are going to contribute reorbits of any fixed index, and so you can, everything is quite concrete. And what they showed is that you get, in this case as well, lovely combinatorial formulas for the capacities. So here are the formulas. So in the case when the toric domain is convex, the kth capacity of x omega is the minimum omega norm of an integer v. So the omega norm is given in here in a natural way, and then you look at all vectors v whose entries are non-negative integers, and those non-negative integers sum to k. So just in practical terms, if one was to compute the kth capacity, one would have to compare the outcomes of these optimization problems defining the omega norm. So there would be k plus n minus 1, choose n minus 1 of these optimization problems. So certainly something a computer could do, but for large k, or for general large k, one has to work a little bit to say something about these numbers. And then there's a similar formula in the concave setting. So if x omega is concave, the kth capacity is now the max over this measurement of v. So here we take the minimum, not over omega, but over the relevant part of the boundary. So you take the boundary of omega, you intersect it with the strictly positive sector and take the closure. So it's pictured below. And then you take the maximum such measurement of V over all V with integer entries, and those integer entries sum to K plus N minus 1. All right, so these were the tools we started with, and then we started asking questions. And so the first set of questions had to do with the relationship between the capacities and the Minkowski sum. So in this direction, there's essentially one fundamental theorem due to Artstein-Avidan and Ostrover, where they established this lovely symplectic analog of the Brunn Minkowski inequality for the first capacity. So this works when U and V are convex bodies in R2n. And then the first capacity of the Minkowski sum of U and V to the power 1/2 is greater than or equal to the first capacity of U to the 1/2 plus the first capacity of V to the 1/2. So, if one replaced C1 by the volume and 1/2 with 1/2n, this would be the Brunn Minkowski inequality. So that's the comparison. And more than this, they prove that equality holds if and only if the representatives of C1 on the boundaries of U and V are homothetic. So rather a complete and beautiful result. Given the foundational nature of the Brunn Minkowski inequality in convex geometry, it's natural to ask whether this type of inequality is a property shared by symplectic capacities in general. So we asked that question, but of the Gutt-Hutchings capacities for K greater than 1. And then we found that, in fact, it holds for none of these. So the first theorem is that for every K, we can find we just work with ellipsoids. We can find 2 ellipsoids where the symplectic analog of the Brunn Minkowski inequality does not hold. What allowed us to get to these examples is the fact that we were able to compute the unknown term here, the kth capacity of the Minkowski sum of 2 symplectic ellipsoids. This came in stages. We first found a nice parameterization of the boundary of the Minkowski sum. And then the optimization problems that appear in the Gutt-Hutchings formulas are somehow manageable for this function. I wrote down the examples here. I won't say them aloud, but there's 2 families of examples, one for even indices and one for odd indices. Some things to note is that for large K, all the ellipsoids are close to the ball, E11, which is perhaps not where you would expect to find counterexamples, because Minkowski sum is not interesting for balls. A ball plus a ball is a ball. But somehow this, and I should say that, of course, the symplectic version of Brunn Minkowski does hold for many ellipsoids. So these are kind of these family of I would say counterexamples, let's say, are not everywhere. They live in special regions, and so finding them is finding families of examples which cover all Ks was the challenge of that work. So in terms of an explanation as to why it fails, this is maybe not so satisfying. I will say that there is some kind of numerical evidence that perhaps the Brunn Minkowski inequality doesn't hold, but something within a correction term might hold, or at least it does in the landscape of ellipsoids, but that's a bit speculative. But if one is looking for an alternative explanation for this failure, Yaron gave one to us, so let me describe the insight that he shared with us. So in the paper that I quoted with Artstein-Avidan, they prove the following result, that any normalized capacity which satisfies the symplectic Brunn Minkowski inequality has the following property. For every centrally symmetric convex body, we have this inequality between the capacity and the mean width. So the capacity of U has to be less than or equal to pi times the mean width of U over 2 squared. So this is a very, I like this inequality a lot. It relates capacities to the mean width, which is one of the classical mixed volumes that appears in Steiner's formula. It's kind of a classical measurement in convex geometry. But nevertheless, one can look at this proposition as a test for a capacity to satisfy the symplectic Brunn Minkowski inequality. So if this inequality can be shown to fail, then the capacity does not have the property that it satisfies the Brunn Minkowski inequality. And so Yaron pointed out to us that if you apply this to the normalization of the Gutt-Hutchings capacities, and if you choose U to be P11, so the symplectic cube, then this geometric inequality will not hold for all k not equal to 3, 5, or 7. So you kind of wipe out almost all cases with this observation, and then you just need examples to cover 3, 5, and 7. All right. All right, so I'm going to skip over the next 2 slides because I'm going a bit slower than I anticipated. So the next set of questions we used the Gutt-Hutchings formulas to approach involved the relationship between capacities and volume. Okay, so if we look at the formulas for the capacities of symplectic ellipsoids, which I quoted before, the capacities as a collection see the number A completely. So that sequence, the sequence of numbers given by the capacities determines A uniquely. So in other words, the capacities see the volume, which is just A over 2 in this simple example. However, if one looks at the other elementary example, P1A, the capacities are equal to K. They are all completely blind to the number A and hence the volume. So we wanted to explore how these blind spots develop. So a natural approach is to consider a sequence of, a family of domains which interpolates between E1A and P1A. So there's a natural choice here. So we'll call it EP1A, given by this formula, which indeed goes from E1A at P equals 1 to P1A as P goes to infinity. And then we want to use the Gutt-Hutchings formula to understand these functions, which can be thought of as functions of K, functions of P, and or functions of A. And so the Gutt-Hutchings formulas reveal quite a bit about these. So the first kind of small result here is that if you fix K and fix A, and think of this as a function of P, then for all sufficient, so to say it in short, the capacity as a function of P is blind to A after some finite P. So there exists some pk less than infinity such that the capacity is constant and equal to k for all p past that point. So the blind spot appears in finite time, if you will, in finite p, and then stays there. More interestingly is the other result which the Gutt-Hutchings formula provides. So if you fix P And think of this as a function of A for a fixed K. For all sufficiently large K, this function of A is strictly increasing. And in fact, you can derive the form of this function as appears in these brackets. So what does this mean? It means that for all large K, the CK is CA. You can invert them and as a function of A and recover A, and hence the volume of the domain EP1A, which of course only depends on A. So the answer to the first question is that as a collection, the Gutt-Hutchings capacities are only blind to the volume in the limit as P goes to infinity. All right. So when you try to put this into context, it looks like you've kind of overcome the worst case scenario. You had this complete blindness to the volume for symplectic polydiscs. And then if you just approximate them by smooth things, you see the volume. So one can ask then, if you start with a star-shaped domain with a smooth boundary, does the collection of the Gutt-Hutchings capacities see the volume? This seems like a reasonable question, and of course that would be remarkable. Of course, we're all familiar with the result of Hutchings, Cristofaro, Gardner, and Ramos, which says that the ECH capacities see the volume, and many incredible implications of that. This would be a shocking starting point if the Gutt-Hutchings capacities also saw the volume, but indeed they do not. But the problem isn't singular boundaries. It turns out that they don't see the volume, but for me to be able to describe that to you, I need to describe a simplification of the Gutt-Hutchings formulas that we derived under an additional symmetry assumption. Okay, so here's the relevant assumption. We say that a domain omega in the non-negative sector of Rn is symmetric if you can take any point in omega and permute its entries, and the result will still be in omega. So very symmetric. And then what we showed is that if omega is symmetric and the corresponding toric domain X omega is convex, then the kth Gutt-Hutchings capacity is just given by one optimization problem. So it's just given by the omega norm of a single vector VKN, where we have this concrete expression for VKN. So we have the floor of K over N, and then the ceiling of K over N. So K mod N times, or the remainder of K mod N times. So this is a much easier thing to work with. And then there's a corresponding formula in the concave case. So let me quote that. So again, if you start with an omega, which is symmetric in the sense described above, and the toric domain is concave, then the kth capacity is given by this single optimization problem. So this omega measurement of V hat Kn, where V hat Kn is this concrete, this specific integer vector with the desired properties. Okay, so I will describe how to make this simplification later, but it's better to describe its uses first. So here's the first setting in which I will use it. So let's consider the convex case. So we'll look at a convex omega defined as the area under a graph of a function little f. And so little f will have these three properties. It will equal its own inverse. That's the same as saying that omega f is symmetric in the sense that we described. We'll say that the second derivative of f is strictly negative. So that gives us convexity of x omega f. And then we'll have this third condition, which is really aesthetic. It just kind of simplifies the formulas to come. So we'll just assume that the derivative of f at 0 is between -1/2 and 0. All right. And so then we define a collection of points. So the first is just the unique fixed point of the function f. So xf, I'll call it. And then we define a sequence of points. So for k odd, we say that xk is defined by this equation, that f prime of xk is equal to minus k minus 1 over k plus 1. So again, the indices here are just odd. So the red xk's are a monotone sequence of points converging to the fixed point xf. That's the way it works out here. Okay, and so with these definitions, we get this very compact formula for the kth capacity of x omega. That should be x omega f. So for all even indices, the kth capacity is just k times the fixed point. And for all odd indices, you just get this simple linear combination of xk and f of xk. All right, that's just a direct application of the formulas, the more general formulas we wrote before. So what does this do? So in pictures, this looks as follows. We have this monotone sequence x1, x3 converging to the fixed point xf. And all the capacities are determined by that sequence and the values of f along that sequence. All right. So as a picture, this is not terribly exotic, but this is turns out to be a great laboratory for analyzing the capacities. They're defined by this non-trivial set of data, which you can see. And we have the freedom to manipulate f. So the conditions on f, the first one is that it's equal to its inverse. So as long as you preserve that kind of closed condition, you're free to manipulate f in the presence of this picture of the data, which determines all the capacities. So you can manipulate them in a very hands-on way. So let me describe such a manipulation. So one thing one can do is the following. So if you perturb f away from this sequence of xk's converging to the fixed point, you can change the volume while keeping the capacities all fixed. This is very simple to do. So what would one do? One just starts with f, and then one adds a bump function away from the data, which determines all the capacities. So you could add a small bump, well, it doesn't have to be small, but the moment you add a bump function whose support lies between two of the points in the sequence. So then we add a scaling lambda. So all this will take place to the left of the fixed point, and to keep the resulting function equal to its inverse, you have to kind of make the mirror change on the other side of the diagonal, so that the graph is symmetric in the diagonal and the function is equal to its inverse. So that's what I mean by adding the mirror bump. So if one does this for all lambda whose norm is sufficiently small, one gets a function f delta, which satisfies the three conditions, f1, f2, and f3. We haven't changed any of the data which determines all the capacities. So the capacities of the new region are equal to the capacities of the old region, but we've quite visibly changed the volume. So if if delta is positive, we've increased the volume. If delta is negative, we've decreased the volume. as we've looked. All right. So this is and we didn't need any singular boundaries to achieve this. This is all just in a smooth a setting where the boundary is smooth. So this is how one can separate the volume and the capacities. But there is some kind of tension here. Of course, we can't deform the volume arbitrarily much. I mean, delta has to be small for this to work. So there's a reasonable question to ask, even after seeing this example. So one can ask if, how much the, sorry, I should answer to this question here. Right, so this question is, how do I know this mirror bump doesn't affect the capacities? So the sequence I wrote in red that converges to XF is all on the left, and the bump would be on the right. So it wouldn't interfere. I hope that's clear.
There's a question.
I was trying to address that
okay.
question with this one.
But I thought you said you had to make it symmetric, both around the point where it intersects the diagonal. So you're
right. So okay. So let me draw it. So I'm sorry it'll disappear, but if you add, let's say the bump here, the symmetric bump will be here.
And you're saying that that's not going to, because it's before X1, it's not going to affect anything.
That's right. That's right.
Right.
No, X1 doesn't move. Sorry. So that you look at the defining, right. So if you look at the defining condition for the XK, it's just where the derivative is equal to that value, and that won't change if your bump, doesn't.
I see. You choose a careful bump so you don't change that condition. Okay.
Yeah, well, that condition is a condition at xk. So if you change the function away from xk, that condition will still hold. That's a condition for the derivative.
I see. And you still have to make it decreasing this function, right?
Yeah. That's where delta has to be small.
Yeah. Thank you.
Okay. Right. So sorry. Right. So I just wanted to mention this question, which I don't know the answer to. So, so again, I just want, so there is this tension that you can only deform the volume so much with this specific tool. And so the real question is there a tool with which you can deform the volume arbitrarily? So this is one way to phrase it without changing the capacities, of course. So this is one way to phrase it. So let's suppose one had a convex body in R2n with a smooth boundary. So it has its capacities, and then one looks at the supremum of the ratios of the volume of V and the volume of W over all domains with all the same Gutt-Hutchings capacities as U. Okay, so so these could be deformations. These could be something more clever that keep the capacities fixed. And the question is, what's the kind of largest? Is the ratio of these volumes bounded? So here I added convex. I can describe to you how without convexity, the answer is no, it's not bounded. You can change the volume arbitrarily. So I think this is also an easy example to share. So I'll share that now. Are there any questions at this point? Maybe I should stop first. Okay. All right. So to describe how the volume can be completely separated from the capacities, one can start as follows. So one starts with a concave toric setting. We'll look at a concave region omega h, so the area under the graph of function h. H will again be symmetric in that it will equal its inverse. Now the second derivative of h would be strictly positive. And here, not just for, well, not just for cosmetic reasons, I'm going to assume that the derivative of h at 0 is finite and less than -2. So here, the simplified versions of the Gutt-Hutchings formulas give us, again, a concrete simple formula for the kth Gutt-Hutchings capacity. So here things are switched in parity. So the odd capacities are a multiple of the fixed point of h. And the even capacities are a linear combination of these points x hat k and the value of h at x hat k when k is even, where x hat k is defined again by this condition, a condition on the derivative. This time it looks like h prime at x hat k is equal to minus k plus 2 over k. So this happens exactly once and defines x hat k uniquely. All right, so if one looks at the corresponding picture in this case, one gets the thing on the left. We get a sequence of x hats now with even indices converging, increasing monotonically to the fixed point. And then in the concave setting, we know, well, okay, so in either setting, all of the relevant information kind of lies in some small part of this, some subset of the graph between these two yellow points. So what does that mean? That means that if we change h outside of these two yellow points and keep the properties of h, the relevant properties of h satisfied, we can change the volume without changing the capacities again. But now we can change the volume arbitrarily. So if we change h by going straight up like this, and then in a mirrored fashion going straight across like this, so if we move sigma in both directions and call that h sigma, it becomes quite clear that with yellow points fixed, we can increase the volume arbitrarily. And so we've created regions with the same capacity, a family of regions with all the same Gutt-Hutchings capacities, but the volume of the new regions, as the parameter sigma goes to infinity, the volume goes to infinity. So they're completely dissociated. All right. All right, so another set of manipulations that one can do involve the capacities themselves. So here the relevant question would be, are the capacities independent measurements? So I guess one could ask, how could they not be? So it might be that, so let's say we're in a generic situation where the boundary of X has the simple closed Reeb orbits on the boundary of X are all non-degenerate and geometrically distinct. Okay. It could be that all the capacities are represented by a finite set of simple closed Reeb orbits and their multiple covers, in which case you couldn't make deformations without changing infinitely many capacities all at once. So that's how they could not be independent, or they could be dependent. So it turns out that they are independent. One can manipulate them one at a time using the similar tools to the ones I've already described. So let me fill in some details here. So let's say we wanted to deform an odd index capacity and leave the other ones fixed. So one could set up the following model. One could consider a convex F, as we did before. So remember, in that setting, the capacities are all determined by this sequence with odd indices converging to the fixed point. And so the jth capacity is determined by xj and the value of f at xj, right? So if we can deform those two quantities and leave the other quantities determining the capacities alone, then we've moved one capacity and not the others. And this is very easy to achieve. So you start with f, and now you put your bump function around xj and away from the other elements of the sequence. You choose, so I chose the bump function to have 0 volume, just because you can. And the value of xj is 1. And then you multiply this by delta again and do the mirror deformation on the other side of the diagonal. And then we've created a new region, x omega f delta. For the capacities not equal of index not equal to j, we haven't changed them. So those capacities are all the same. They're all determined by the things that we didn't touch. The jth capacity is now increased. Xj hasn't changed. We didn't change the derivative of f delta at xj. The derivative of the thing we added was 0. So we haven't changed the derivative of f delta at xj, but we have changed the value of f delta at xj. And so the jth capacity changes by exactly in proportion to that. So we've manipulated one capacity at a time. And because we chose our deformation to have 0 volume, we've actually kept the volume constant during this, the deformations of the capacities. Okay, so this is the model for odd capacities. For even capacities, there's a similar model. Perhaps I won't go through the details there just because they're identical, except you start with a concave function. So one thing these models don't do is provide a setting in which, a single setting in which any capacity could be deformed independently. In one model, we could do the odd capacities. In one model, we could do the even capacities. And so I wasn't clever enough to find an example where one could do even or odd in the same model. So I'd like, that's something I would look for in the future or be very happy to hear about. All right. So the next question we addressed, which is actually the first question we had in mind, is the following. So we know that the Gutt-Hutchings capacities and the volume are independent measurements. So one can ask, if you take them together, are they a complete set of symplectic invariants? Do they determine any nice class of subsets up to symplectomorphism? Here's the strongest version of this question that we can address. So let's suppose we have a U which has a smooth boundary and is strictly convex. Okay. The question is, do the Gutt-Hutchings capacities of U and the volume of U determine U up to symplectomorphism? So this is some version of the recognition question. And so using the techniques I've described, one can answer this in the negative. One can say, no, this is not true. So one needs better tools to do this. So we need to introduce new tools at this stage. So we'll use the embedded contact homology capacities introduced by Hutchings, as well as the algorithm for computing them for concave toric domains, as we've been discussing. So that algorithm was developed by Choi, Cristofaro, Gardner, Frankel, Hutchings, and Ramos. Okay, so let me describe the strategy for, so really we're going to produce a counterexample. So we're going to produce two strictly convex domains in R4 with smooth boundary, whose capacities are all equal, whose volumes are equal, but which are not symplectomorphic, the ECH capacities will tell them apart. Okay, so let me describe this construction. So let me start with the strategy of the construction. So we'll start with the model we've already described, where we have a concave toric domain X omega H, as we discussed previously. And then we notice that, so now we want deformations which keep the capacities the same and the volume the same. So this is easy to achieve in a similar way. We add a kind of a balanced bump with no volume, but we add it away from the sequence of x hat k's converging to the fixed point, so that this doesn't change any of the capacities. And because it's balanced, it doesn't change the volume. And then the task would be to show that x omega h delta is not symplectomorphic to x omega h. We want the ECH capacities to tell them apart. So we want the existence of this bump to imply that one of the ECH capacities tells these two regions apart. So why would one suspect that's true? Well, I mentioned before this result of Hutchings, Cristofaro, Gardner, and Ramos, that the ECH capacities see the volume. So if one does just this part, if one does this deformation, you're changing the volume. So you expect an ECH capacity to see that kind of deformation. And you also expect it to see such a deformation. And so that is the intuition. And in fact, this turns out to be the case. More generally, one expects that the ECH capacities, the algorithm to define them, will depend on a dense set of points on the graph of the function, is really what's happening. Okay, so that's the strategy. And then, so in our work with Liang, we just realized it in a specific example, a concrete example, which I'll just give you the quick outline of. Okay, so we started with the following concave domain. So the function here is defined as the image of a curve. So this curve appears in the work of Ramos, who proved that the interior of the corresponding concave toric domain is symplectomorphic to the interior of the Lagrangian bidisk, which is of course a beautiful result, but it's not why we chose this. We chose this because this curve has nice computational properties. It's easy to turn the crank of the algorithm to compute the ECH capacities for this particular curve. So that's why we chose it. So it suits our purposes in that way. In another way, it doesn't. So the boundary of the toric domain of this curve is not smooth. So we have to fix that with a simple translation. We just take that graph and we push it down diagonally so that it doesn't intersect the boundaries. It doesn't intersect the axes obliquely. So now the domain under the blue curve has a smooth, the toric domain corresponding to the area under the blue curve has a smooth boundary now. And we'll think of that as the graph of a function h. And then one has to analyze the algorithm for computing the ECH capacities. So here we have a symmetric region, so that algorithm simplifies in useful ways. I won't get into the details of the algorithm just because it's easy enough just to talk about the relevant ones. So the algorithm, the first part of the algorithm, one way to describe it is to identify a collection of points in the domain of the function h corresponding to a nice subdivision of the area. So because this region is symmetric, these points can be labeled with ones and twos, so ordered collections of ones and twos. Okay, and so if I go back to the intuition I alluded to before, one would expect that the collection of all these points would be dense in the domain of the function h. And so, so for this particular curve, one can write down, any collection of these special points, and one just stops as soon as one gets to one which is not in the sequence of points determining the Gutt-Hutchings capacities. So it turns out that, I think I said in the next page. So x22, this point involved in the algorithm to compute the ECH capacities, lies away from the sequence we've identified, which computes the Gutt-Hutchings capacities. Okay, so now we carry on with the strategy we described. We add this balanced bump, but now we change the value of our function at x22. Okay, so this doesn't change any of the capacities because of the location. This doesn't change the volume because of the shape. But if one looks at the algorithm, it does have the potential to change one of the ECH capacities. And so, in fact, one can check that it does. In this case, it ends up changing the 9th ECH capacity by delta. And that's enough to settle things. So we've got two regions, x omega h, and then the deformation, which has the same Gutt-Hutchings capacities and the same volume, but now its 9th ECH capacity is different. So these cannot be symplectic. All right, and so this is kind of, there's nothing special about the choices we made. They just happen to be convenient to, to visibly achieve the goal. But this is kind of a robust strategy for computing these kind of pairs of things. All right. Any questions on that construction? Okay. So because it kind of leads to the pictures which allow us to do these kind of hands-on manipulations, let me briefly describe the proof of the simplified formulas that I've been using. So this is really Yuanpu's proof. This is really his work. So let me describe it to you. Again, the simple task is to take the original Gutt-Hutchings formula, which is this, so to compute the kth capacity of let's say a convex toric domain. I'll describe the convex case. One needs to take the minimum of the omega norms of V over this collection of V's. And we want to show that if omega is symmetric, that this can be reduced to a single term. Okay. So the idea is very simple. So let's just say that an n tuple is ordered, an element of Rn is ordered if the entries are ordered by size. So in particular, Vkn is ordered, right? It was some copies of the floor of k over n, and then some copies of the ceiling. So it is ordered in this sense. In this setting, symmetry of omega implies the following, that the omega norm of V is equal to the omega norm of any vector obtained from V by permuting its entries in any way, right? This is easy to deduce. So that means that in the Gutt-Hutchings formula for the capacity, one can minimize only over ordered integer vectors satisfying the relevant conditions. So in pictures, instead of looking for the minimum omega norm over everything on this line, we can cut out a large part of them. So in this dimension, roughly half of them, but in other dimensions, much more of them. All right, so that's useful, but certainly doesn't get us there. So then the key observation is that you can kind of reduce this to a contraction mapping argument or something close to that in this setting. So let's consider the map T. So I wrote it but didn't say it. So S arrow Kn is the set of relevant integer vectors. So their sum of the entries is equal to K, but now we're just restricting to the ordered ones. Okay, so in the picture, it's just the things that are left. All right, so on this set S arrow Kn, there's a map which is close to a contraction mapping with respect to the omega. And it does the following. So let's take, if one starts with a vector in S arrow Kn, it has integer entries. They're ordered. So let's say that the first little m of them are the same. The smallest ones are the same. And the biggest ones, big M of them are the same. So we have this form, general form, little m could be 1, big M could be 1. All right. And then we have this map T, which will take a 1 from here and move it over here if it can. So if Vn is at least 2 bigger than V1, we can do this and still remain in the set S hat Kn. Okay, so that's what we do if that condition is satisfied. If that condition is not satisfied, we don't do anything. But there's only one starting point for which that condition is not satisfied. It's our vector Vkn, where we just have floor, certain number of copies of the floor, and then a certain number of copies of the ceiling. So the fixed point of this map is this special vector Vkn, which appears in the simplified formula. And then more than that, so there's a finite number of these vectors in S arrow Kn. So if we apply T enough times, we'll get to Vkn. Okay, so it's all right. And then, right, so in pictures, the map looks like this. It's moving down and its fixed point is this 1 point Vkn. And then the nice observation at this point is that this map T doesn't strictly decrease the omega norm, but it never increases it. And that's enough to get to the simplified version of things. So if you're at some minimum as prescribed by the Gutt-Hutchings formula, and you apply T to it, this result tells you that that's still a minimum. Okay, and so you can keep on applying T to your original minimum, and eventually you'll get to Vkn, which will also have to be a minimum, which was kind of the claim of the simplified formula. All right, so I think I shouldn't start anything beyond that, so I'll stop talking there.
Thank you very much. Are there any questions? So I have one question about, so there was the question you stated about whether you can change the volume arbitrarily for convex domains, keeping the capacities fixed. And then you showed an example with concave toric domains.
Yeah. So
do you know
so it's concave toric, but that happens to be also convex in R2n.
Yes, so that was my question.
Yes, yes. Yeah.
So these are convex in R2n?
Yeah, so I mean, it doesn't look like it, but when you take straight lines in R2n and you project them to the toric picture, they become concave.
Right.
So this is yeah, this is not steep enough to ruin that property.
So the question is, so can you go back to the slide about your, so
Oh,
what was the question? Sorry, that's my.
My screen changed.
It's not, yeah, it's not shared anymore.
All right. All right, sorry. Oh, sorry. I didn't answer your question correctly. So I did show a way in which you could arbitrarily increase the volume by kind of putting the ends out to infinity. Eventually, that will stop being, even if you start off convex in R2n, eventually that will stop being convex in R2n.
Okay.
So it still makes sense. So you can't increase the volume arbitrarily within the convex, under the convex assumption.
But you can, I see. So, but the ratio could be like, for each number, you could cook up an example with ratio
Which gets
larger
large,
than
yes.
this number.
Yeah.
I see.
Yeah.
So then the question is.
Yeah, so I mean, right. So this is the question you were asking about. Right, so whether convex is so I mean, I only chose convex because I knew in the examples to come, I would ruin convexity eventually when I increase the volume past some certain point. Whether there's a better assumption to make in this question is certainly.
So do I understand correctly that the supremum over the
ratios,
U's
yeah,
that are convex is infinity?
I
mean, up to some like limiting the volume, right? So convex domains of volume.
It's likely, but I haven't worked out examples which verify that, but it's like it's possible.
I see. Thank you.
Yeah.
I think this question once was already addressed at this seminar. So is there any way to understand what is different with the sequence of capacities for non-toric domains? So if you make kind of perturbation which creates chaotic, at least pieces of chaotic dynamics on the boundary, so can you detect this in any way?
I cannot. I would love to, but right. I mean, yeah. So there are. No, I don't know how to do it. I mean, you'd have to start with. Maybe I don't understand the true content of the question, but you'd have to start with some formula for the capacities, right? And to see how it varies, or what is the starting point?
I think you're doing the okay. So a picture which I have in mind is the following. So let's think about geodetic flow on the torus, right? So you have Euclidean geodetic flow, right? So affiliation by Lagrangian tori, like you have here, at least locally, right? And so then you make a kind of add a bump to the metric.
To the metric, right?
Yeah, the story disappear and you get some chaotic piece inside the dynamics, right? And so then you can glue it probably back.
Well, so there's probably a version of that which is approachable. I mean, so we know that C1 is the action of the smallest closed Reed orbit, right? And so in a family, you could probably follow that around and see how it changes. And then for C2, well, sometimes you can identify it and sometimes you can't. Well, very rarely you can identify it. So the only work I know of where this is done is for the Lagrangian bidisk by a trio of Italian authors whose names I can't remember. Facina is one of them, where they compute the second and third Ecklen-Hofer capacities just by looking at the action spectrum. So if you're in a setting where you can identify the capacities just by the nature of the action spectrum, like you might be able to do if you have a bump in a metric, then maybe you could say something about an actual deformation. But I'm not aware of tools which would address that beyond that.
I see.
I
Okay.
think you can see the toric domains are special because if you look at barcodes, the endpoints of most of the bars are doubled in a certain sense, because roughly speaking, there's sort of two orbits, two wave orbits for each. At least in the four-dimensional case, you have these tori, more spot tori, which after perturbation become two wave orbits whose actions are very close. So, the actions, these sort of action spectrum, if you like, or the endpoints of barcodes are all doubled, and then that will not be the case if you perturb to make it not toric.
Right, so you doubled in dimension 4, right? So in higher dimensions, it will be different material. Okay, understood what you say. Okay.
Yeah.
It's very nice.
Are there any other questions? If not, then we can thank Ely again. Thank you very much.